Good morning, everyone. Welcome to today's webinar entitled RAN Dimensioning Lessons Learned by Telstra, sponsored by Ascom. My name is Adlan Fela, and I'll be the moderator today for this webinar. We have a very dense agenda today, so we'll get through some housekeeping slides very quickly in terms of how to use this tool here. So on your right side, there is a control panel that you can use to open and close the panel between full screen and window mode. The audio pane allows you to select between audio setup and microphone speakers. Please submit your questions throughout the webinar in the questions box, and we'll be reviewing them as we advance in today's webinar. Commonly asked questions: can obtain the slides? Yes, the webinar is being recorded and the slides will be made available today. The agenda for today is the following. We'll start off with some market trends overview from Caroline Gabriel, Research Director at Maravedis We Think, which we then pass on to Max Doney, who will dive into Telstra experience with RAN dimensioning. And then Bruce Northcote will follow up and provide his insights on the tool. All of this will be followed by a 10-minute Q&A at the end of the webinar. So without further ado, we pass it on to Caroline.
Thank you, Adelaine. Lovely. Welcome, everybody. As Adelaine said, I'm Caroline Gabriel. I'm Research Director at Maravedis We Think, and I'm just going to take about 10 minutes to set out some of the key trends that we're seeing in this area, which relate to the operator's huge challenge of deploying enough capacity to keep customers happy at a cost level that still enables them to make a profit, even at a time of falling ARPUs in many services. Here we talk on an ongoing basis to many types of service providers, including a core research base of about 75 mobile operator groups worldwide, and they provide us with detailed inputs into their plans for network deployments and the business case that they'll support. This in turn feeds into our 5-year forecasting model for mobile and also Wi-Fi networks. The patterns we've seen since embarking on this activity, which was more than a decade ago now, have changed considerably as the levels of data traffic have exploded and the applications in use have changed. We're seeing social media, Internet of Things. All these things mean that networks are having to behave in an entirely different way. So it's not just about sheer capacity, it's about behaviour and planning. This will have a profound effect on how mobile networks are deployed long before we even get to 5G. The capacity crunch or capacity explosion, I think, is something that's talked about a lot, and we all understand it. However, there's also, in parallel, a revenue crunch. We can see from the slide on the right, it's based on consensus from a wide survey of mobile operators, and you see lots of slides similar to this, but the basic message of it is fairly clear. As we carry on with traditional 3G style macro ways of deploying and planning a network, capacity investment to meet growing data demand over the next 5 years or so is not justified by the incremental revenues that increased data will generate. In fact, on average, using traditional methods, it will take 5 years before those revenues actually start to give an ROI on additional capacity. That's a very long time in a very fast-moving market, and this doesn't take into account the fact that at the end of those 5 years, we can be sure there'll be some new services and behaviours that have not even been thought of. So a new approach to the access network and the network as a whole is essential. Operators have to look for new ways to increase real capacity, just throwing hardware and extra cells at it is capex heavy at a time when most operators are under a lot of pressure on their spending. And it is a law of diminishing returns. Without very clever tools, just adding cells can create more problems than it solves. Hardware on its own does not scale linearly, particularly at the macro level. So there's a new focus on optimizing the assets that operators already have, managing resources flexibly, squeezing the maximum capacity out of the hardware that's there, and planning very carefully when they add any new cells. We're going to hear a lot about this in the webinar today, but the key is soft capacity, dynamic capacity that can be allocated where it's needed on an ever-changing basis. And that really is key to the survival of the mobile operator model at a time when there are alternatives to the mobile operators, perhaps for the first time. Other carriers out there that perhaps have lower cost, total cost of ownership. They may be very heavily using Wi-Fi, for instance. So there are different cost models and different network types emerging. The mobile operators know that LTE has a lot of advantages, but they are going to have to plan it in a different way that reduces cost of ownership. And while they're thinking about that, there are two very key differences when optimizing a network compared to the past, 2G and 3G. There are far more elements that need optimizing. It's a much more complex task when you're actually dimensioning an access network. And there are quite different business objectives, which are being heavily driven by the customer experience, as we'll explore briefly now. So on the first point, the RAN actually looks extremely different. There are far, far more elements being added all the time. There's a need to dimension and optimize many different types of cell equipment, and so it's not a question of relatively uniform macro cells on the same sorts of towers. We can see from the graph on the right, this is a survey, the percentage of carriers who are picking various broad RAN architectures as being the key drivers for their 5-year plan of deployment. And you can see it does change over time, but the message is that lots of new architectures are coming into play. The traditional macro-first architecture certainly isn't going away, but it becomes mingled in with other approaches. There's Wi-Fi being added in. There's many, many small cells. We can see the figures on the left. And we're moving towards Cloud RAN virtualization. All this combined with changes at the macro layer too, massive MIMO. Many, many elements are coming into the RAN, and there's the danger that you add capacity but in a chaotic way if all these many items are not properly planned, dimensioned, coordinated, and so on. And on the second point, when considering how to plan and optimize a mobile network, the KPIs that operators are looking at are shifting quite considerably, and certainly the more advanced and forward-thinking mobile operators are increasingly thinking of the customer's real experience of the network as opposed to the sort of technical view of how the network is performing. So it's quite easy to look at a screen with some tools and see that, yes, you've got roughly the right number of cells for the population and they're not interfering with one another, and there's the correct amount of coverage and capacity for a certain area, and it all looks rather nice. But of course, since a lot of the point of these networks is that they're mobile and the users are mobile, and as we pointed out earlier, they're behaving in many, many different ways now. Social media, for instance, creates an awful lot of signaling traffic. So it's not just about where the users are, it's about what they're doing, how they're moving around. So they may well find a spot that's extremely congested, and they will get a very bad experience from that, even though theoretically the network is well provisioned and well planned. So operators are getting this. They're seeing that capacity is not an end in itself. They've got to ensure that for the maximum time, their subscribers are getting a really good real-world experience. So we're seeing far fewer operators measuring their RAN success in the traditional way with the 3 Cs, cost, capacity, coverage. The sheer capex cost considerations of the hardware are shifting towards total cost of ownership, including the whole of the network, but also return on investment. And that puts the shift heavily onto software I think sometimes in the past, tools like optimization have been seen as a sort of additional overhead or something that should be just bundled in with the hardware. Now they're often seen as actually something that carries lower capex than additional hardware, but can significantly affect the ROI, therefore justifying a bit of extra spend. Overall quality of experience, that's becoming the key competitive differentiator. You can see in the graph, this was a survey of MNOs carried out in March. They were asked to give their top 5 most important KPIs for their business model, and then among those 5, they were asked to rate the one that was the most important. And you can see that quality of experience, it comes into the top 2, and this is very different from what we would have seen a few years ago. And this is because operators are always very fixated, naturally, on churn. They want to attract but also retain customers. We all know that attracting a new customer costs a lot more than retaining and keeping one happy that you already have. So after sheer cost considerations, quality of experience is becoming the key driver, and they see that a poor quality of experience for a customer is the second largest reason for them to churn after the actual data rates and the data tariffs. And QA, it's not just about defensive retention. It may also support higher ARPUs at a time when overall ARPUs are falling. Because if you have a network on which a certain level of quality of service can be guaranteed, you're in a far better position to support enterprise services, for instance, that may come with SLAs, public safety services, and very QoS-dependent services like streaming video at a good quality. And so operators are not just thinking about sheer capacity, they're thinking about distinguishing high-value customers, high-value applications, and dimensioning the network to be suitable to those because they will generate the most revenue. What are the key ways to achieve that high level of quality of experience? As I've repeatedly said, it's not just about hurling capacity at the problem. In fact, there are large amounts of capacity in most networks that are locked up by static architectures. So in one cell may be extremely well provisioned, but nobody goes to it. Another one completely congested, and there are sort of limited ways to shuffle that capacity around if the network is paving in a traditional way. So there are significant ways to make more from current networks and to plan new ones more efficiently, more flexibly. Unlock the soft capacity, the underused resources that are in the network as you build it out. Map capacity to demand by time of day, which changes by the location of the largest number of users or of the highest value users, by the type of application and the sort of way that it behaves on the network. Dimensioning is important, but it's part of a broad optimization picture. We're seeing operators using a wide range of tools to balance their networks and make them maximally efficient. And then moves to, there's a lot of data, of course, emerging from all this about the way that users on the RAN are behaving. So linking that into OSS, BSS systems, particularly things like customer experience management. So you not only know the experience a customer is having, but then link it to the kind of services that you deliver to them, or perhaps to, if something's going wrong, perhaps to a proactive kind of apology or compensation to them. And all this leads towards a happy world of fully dynamic resource allocation, where you really can move the network resource that you have to exactly where it's needed. And the results? Cost savings, because the capacity is going where it's needed. You don't have to over-provision everything. You may defer capex on extra hardware because the network you have is behaving more efficiently. Higher customer satisfaction, which leads to lower churn, but also increased ARPU, increased usage. And support for brand new business cases that are QoS dependent, and that includes some of the applications within the Internet of Things that, of course, is a great opportunity at the moment for a lot of mobile operators. So I'm just going to sum up with this slide, which is really meant to summarize the shift in the approach that we're seeing among mobile operators and their priorities when they look at managing and expanding their access networks. So we're moving from, on the left, a very traditional approach to dimensioning, of course, that will always happen. It's not that that process is going away, but instead of that being the central sort of objective of the process, just to calculate quite theoretically the right number of sites and then deploy them, instead your starting point is on the right. A very extreme example, but what is my customer actually experiencing? How can I improve that? And the example here are the Japanese operators monitoring call instability on the bullet trains, the fastest trains in the world, so incredibly challenging for the mobile environment. But clearly this sort of measurement shows that these operators are seeing call instability as a critical KPI and a way as something that will affect their customers' experience and loyalty. So with that, I hope visual summary of the change in priorities at operators, I'm going to hand on to a real-life operator, to Max Downey from Telstra, to explain how his company is approaching.
G'day, my name's Max. I've got a PhD in wireless networking and have spent the past 8 years as a capacity subject matter expert with Telstra, the largest mobile network in Australia. The purpose of this presentation today, which I'm going to cover in about the space of 15 minutes or so, is just to discuss some of the interesting things that I've picked up and noticed while designing capacity models and acting as a subject matter expert over the last 8 years. It's a bit beyond the scope of this presentation to get particularly technical, but hopefully I'll be able to impart some of the flavour of what an actual operator considers when they're going about the RAN dimensioning processes. Finally, I'm an engineer, so this presentation is going to be unabashedly presented from an engineer's perspective. I'm sure if it were presented by marketing or the people who actually control the finances, there might be a subtly different take on things. So, capacity, network expansions, why? At some point down the road, after you've built your shiny new greenfield network and launched it to the grateful public, you're going to notice the network performance start to degrade. Users are going to get less than they were getting. If you've got enough customers, and let's face it, that's the ultimate goal of the game, then your network's going to get congested. And unless you want to suck it up, you're probably going to have to do something about it. You're going to have to expand your network, split cells, add new hardware, add second carriers, build new sites, just do typical RAN-related capacity stuff. But with limited funds, which sites do you expand? Where do you add the new hardware? What spectrum do you add, and so forth? If the people who won't control, if the people who control the purse strings won't give us limitless money, curse them. We'll have to be selective in what we choose to spend our money on. And if we're being selective, then we have to balance a number of competing goals. And these are just general goals. Other organisations might try to balance other things, but they seem to be a sort of a fairly reasonable set of goals. We want to maximise the customer experience. We want to make and do that for the largest number of possible customers. So we want to make as many people as happy as possible. But we want to do this with effectively with our capital. We don't want to throw money where it's not going to give us a good return on our investment. And we can do this through the prioritised expansion of network hardware driven by the needs of the business. And to do this effectively and rigorously and well, we have to have good tools supporting us and well-defined processes and procedures. So this diagram here shows a fairly typical capacity flow, capacity process flow. So at the top, you've got the person with the money, Mr. Moneybags. He's the person telling the engineers, and us engineers tend to be a fairly conservative breed of person. He's the person telling us that we're not allowed to gold plate the network, that we've got to be a bit judicious with the sorts of expansions that we choose to do, because nothing would make an engineer happier than having a pristine network that's operating perfectly. And he's also, or a related department, the person who should be providing the engineering department with the specific requirements of the business at any given point in time. This is the direction the network is aiming to head in, whether it's a cheap and cheerful network or whether we want to be the best in video. These business requirements can be something as specific as we want to ensure that our customers never get blocked more than X% of the time, or something vaguer like we want to make sure that all of the customers who are sitting in their homes have a user experience that is sufficient for streaming HD video and things like that. Given those requirements, it's then the responsibility of the engineering department to have processes and procedures in place to translate these business requirements into specific actions. That is, from a capacity perspective, we need to decide which network elements we need to expand so that we can best meet those business requirements and give us the biggest bang for our buck. In order to be able to do this effectively, it's important that our capacity models and our capacity processes are able to reflect the sorts of things that are being described in business requirements. And typically this means that our capacity models and our capacity processes have to be focused on things like user experience rather than more standard or typical things like network utilization. We want to be describing network performance based on the way that the user perceives the network. We don't want to be dimensioning the network because we've run out of power or we've used up too many codes, because that doesn't lead to a consistent user experience, and it doesn't allow us to make Mr. Moneybags happy. So we need good processes and models that are able to reflect those things, and these actions. Once we've got those and we translate those business requirements into capacity actions, so we effectively generate a scenario list that says, in order to meet these business requirements, we need to do these things. We can feed this list back to the person with the money so that they can have a better understanding as to what the actual cost of those business requirements that they specified are, or we can pass them on and they become actually realized capacity expansions. So they get legitimately deployed in the field and result in sites being built or sectors being split, whatever. And then finally, to complete the loop, we also need to be able to accurately monitor our network performance with respect to the specific KPIs or business requirements that the network's being dimensioned to. This is a really, really important point because there's no point promising that you're going to do something if you're unable to actually monitor it or validate that you're actually doing it. So, how do you translate these business requirements into capacity actions that can be used for financial forecasting or turned into legitimate deployments? There typically tend to be two main general approaches. There's something that I call intrinsic analysis, which is a typically tool-based approach where you use analytic techniques or have some sort of simulation that is able to model and forecast network performance based on an understanding of what the networks are doing today. So an intrinsic approach might take a bunch of network counters and network configuration and crunch the data and spit out a list of sites that need to be expanded. So it's a largely automated process. And hopefully the list of sites that it spits out is in an order that reflects the business requirements as given to us by the guys who control the money. And then on the other side of the spectrum, there's a thing that we call extrinsic analysis, which is really just bringing a bunch of humans into the loop and relying on their local experience, domain knowledge, and just general human grey matter to determine which sites need to be expanded in order to best achieve the specific goals of the business. So you've got an automated intrinsic approach, or a tool-based intrinsic approach, which is either analytic techniques or teletraffic simulations, and you've got an extrinsic approach, which is a qualitative approach based on sort of a human interpretation of the business goals and local domain knowledge. So what we tend to find is that things tend to work best when you use a combination of both. Use a combination of both intrinsic and extrinsic analysis. You let a tool generate a first cut of the network elements or network actions that should be investigated for expansion, and then you bring some flesh and blood into the loop. You let humans vet the list and modify it according to their interpretation of the business requirements and their local knowledge of the environment and their understanding of the technology. We tend to find that the intrinsic prioritization narrows the scope of the things that need to be investigated, but having actual humans vet it is important, because there is no substitute for human expertise and local domain knowledge. But there are many other ways to actually do this. There is no reason why you couldn't rely entirely on intrinsic prioritization. Or if OPEX wasn't a concern at all, why you couldn't rely entirely on extrinsic prioritization. But for bang for your buck, utilizing both to get the best result tends to work fairly well. So that's a very quick overview of what we aim to do with capacity processes and the sort of process that we tend to follow. It's a tricky thing. It's certainly harder today than it was 10 or 20 years ago, because network complexity is increasing. It used to be that you could dimension an AMPS network using nothing but a piece of paper, a pencil, and your old trusty Erlang B formula with a bit of time to kill on a rainy Saturday afternoon. But no longer. With GSM, data gets added to the mix, and suddenly Erlang B doesn't cut it. There are multiple services to balance. So in an edge network, the amount of data that you're carrying affects the quality of the voice that you can carry, or the capacity of the voice that you can carry, and vice versa. It's more complex. So people dimensioning GSM networks probably had a hissy fit at their Erlang B formula and their pencil and paper, and degenerated into a slightly more complex Excel-based analytic approach. And then along comes a little upstart WCDMA with even more services. It's got voice and R99 data, SMS, CS64 video, HSDPA, EUL, all competing for capacity and all taking capacity from one another. It's an incredibly complex system with many incredibly complex services. And to do any justice to it, you need more sophisticated and complex modeling techniques. And this trend continues with LTE, which is yet more complex, and moving into 2020 with 5G, with the Internet of Things, HETnets, machine-to-machine communication. The scope and complexity of the networks that we're attempting to model or to dimension is ever increasing, and it's becoming a very tricky thing. So the tools are required to dimension a network, and the specific domains of knowledge required by the engineers monitoring the network also needs to become more complex and to evolve. It's a really hard area to keep on top of, and it doesn't show any sign of abating. So, compounding the network complexity and the issues that causes us is traffic growth, which tends to be growing almost exponentially, and also doesn't show any sign of abating. The network vendors have been telling us for years and years and years that traffic's going to be growing exponentially, and I suppose 10 years ago I might not have believed them, but it's a truth that has been borne out. So this traffic growth, and this really rapid exponential traffic growth makes things tricky. It means that we can't be complacent. Even if you've got a network and it's performing well now, the pace of traffic growth means that if you don't have appropriate processes in place, then by the time that you notice that something's gone wrong, that some of your cells are starting to get a little bit congested, then it's likely already too late. Has been demonstrated time and time again to the chagrin of many carriers. It's too late to start implementing rigorous capacity processes when you've begun to notice that you've got a problem. It's something that you need to do ahead of time. It's something that takes a little bit of time to get right. And as soon as your network starts breaking, the momentum of that can have devastating consequences on your user experience. So you need to have these capacity processes in place from day dot or as close to day dot so that you can respond to any challenges or changes in behavior in as agile a manner as you possibly can. So at the same time as network complexity is increasing and the amount of traffic's growing, the number of network elements is also increasing. We've got things like microcells and picocells, femtocells, hetnets, network densities as high as it's ever been, and is increasing an absolutely mammoth rate. And this tends to be in response to the increasing capacity requirements driven by the increased data we just saw before. We're no longer in a situation where an AMPS engineer can have an in-depth knowledge of each and every cell in the network. These days we're dealing with networks that have hundreds of thousands of unique network elements. And this has fairly profound consequences on the way that you need to manage your capacity process and manage the sorts of data that it generates. If you attempt to do it and do it in a rigorous manner, then tools like Excel would collapse under the sheer weight of the data. I mean, Excel's not a database. As your network grows, and I really hate to use the term, but to do things properly, you've got to start using big data-esque technologies, or at the very least, sort of proper relational databases to manage your capacity and performance information. So you need properly developed tools. Stuff that's been hacked together in an afternoon by a board engineer is less and less appropriate and will cause greater and greater overheads in the actual execution of capacity processes. So the final nail into sort of damning these network complexity and capacity processes is the increased complexity of products that we're introducing into our network. These products are things like VoLTE, so voice over LTE, and ViLTE, so-called video over LTE, eMBMS, so LTE broadcast, or any form of differentiated QoS where you try and give one group of users a differentiated level of performance as compared to a different level of a different group of users. All these different products require or demand different user experiences, and to do them justice and to meet the business requirements as will be given by the business, we need different capacity models. They need to be dimensioned in different ways, and these product constructs aren't going to stop coming our way. So the capacity models that you use to drive your network dimensioning need to be constantly evolving. Even if you're just doing fairly typical software upgrades, you can't activate network features that are designed to improve network capacity and expect to save money if they're not reflected in your capacity processes. So if you've got a feature, for example, that increases capacity by 10%, say you turn on 4x2 MIMO. If your capacity models don't reflect that in the additional capacity that those cells have, then it's as though you haven't turned on those features, at least from the point of view of actually spending CapEx. And finally, Just to summarise, and Bruce, the speaker after me, will go into this in a great amount of detail. A good capacity model or good capacity processes should, in my opinion, consider the following three fundamental things. They should be capable of performing just-in-time capacity expansions, or what we mean here is that we need to know ahead of time that a given cell or a given site is going to run out of capacity, and know with sufficient lead time that we're able to actually build the hardware at the point of which we will stop meeting our KPIs. This means that it's not sufficient to just monitor network performance. For example, by the time that you start noticing any significant amount of voice blocking on a cell, it's already too late because capacity expansions tend to have reasonably large lead times in the order of months. If you initiate the capacity expansion when you've noticed some blocking, then you're going to have to endure 6 months of blocking until you can actually rectify it. Second is we need to perform all of our dimensioning with respect to user experience KPIs. And this is very important so that we can really respect the business requirements as given to us by the people who are controlling the money or the desires of the business. This means that we want to talk about things from a user perspective as opposed to a network perspective. We want to be able to talk about things like video quality, user throughputs, blocking, as opposed to things like power utilization, code utilization, or noise rise. And this allows us to, as I said before, respect the business requirements and also provide a consistent user experience from cell to cell. And the final thing that we need to do is we need to be able to model soft capacity. And what we mean, or what I mean by soft capacity, is the fact that with these data-oriented services that have link adaptation and are able to change the modulation encoding scheme depending on the radio conditions of the UEs in the cells, we have situations where some cells have much larger capacity than other cells. And it's very easy to visualize this. Imagine a cell where a bunch of the mobile users are very close in. These users can talk to the cell at a very low power because the signal only has a short way to go, and thus the cell can support many of those mobile users. Whereas a cell in a much less forgiving environment with users many kilometers away might only be able to support 1 or 2 users because it needs to use a vast amount more power to talk to those users. So our capacity models need to be able to identify those cells that have large capacity and say, oh, we're not going to need to dimension this cell until its traffic reaches a much larger threshold than those cells which have a very small amount of capacity. In order to do this properly, we need to be able to estimate the capacity of each and every cell in our network. And that's really all I had to say. So I believe that Bruce gets to talk next.
Thank you, Max. Before I pass it on to Bruce, I would like to launch the poll. And we want to ask you, the audience, a question. Do you have a method to take into account soft capacity when determining whether a cell/carrier needs expansion? So we'd like to give the audience a few seconds to answer this question. Thank you.
The introductions. I'm Dr. Bruce Northcote. I'm the CEO of Talari. That's the development group behind Thames Capacity Manager. That's within the Ascom portfolio. Telstra is our foundation client, and we've worked very closely with them in the development of this product. It's all about dimensioning capacity to user experience. I'm going to take a little bit of a step backwards, start slowly and build up quickly towards the end, hopefully. What do we mean by capacity first? If I've got a car engine, capacity of that car engine isn't the highest speed that I can go before it blows up. There needs to be some engineering perspective put in place prior to that. So if we're talking about communication networks, in the early days, if you had a desire to have a phone call, you actually had a dedicated circuit between yourself and the person you're calling. Capacity then could really be measured by the density of wires on the poles, I guess. Following that, we entered the switchboard age, and we had women, or predominantly women, I don't want to be too sexist, but I think it was, that switched calls, patched calls between different circuits. So the capacity then of that particular system came into account was how quickly those women could patch those calls through. Before the electronic switchboard came into being, these women end up being given roller skates because the patches on those switchboards were so large they had to roller skate between them. So capacity has different meanings. Basically, if we have a system, a phone system in which we're offering load to it, for as long as all that offered load is being carried, we've got zero loss. But at some point, the very next bit of load offering into this phone system is going to get lost. At that point, we're measuring 100% user satisfaction, and we can define that as the zero loss capacity limit. Obviously, we're going to keep growing and offering more load into the system, and that's going to somehow hit some asymptote where there's an absolute maximum system capacity. At that point, no matter how much more load we put into the system just can't carry it anymore. That point is the lowest user satisfaction level. So to dimension this communication system, we want to set some target KPIs. In this particular case, we might set a target KPI as we aim to lose no more than 5% of the offered load. In that case, we can dimension to a capacity target, and this yellow star on the y-axis would be that dimensioned capacity target, such that I know if the measured carried load rises above that yellow star, then I'm not going to be meeting my target KPIs. What I've really got then is some safe operating range, or what I've defined to be an admission region. The idea then is that you're constantly monitoring your system and you're measuring how much you're carrying, so that if the green cross there on the graph is my current measured load, then I know that I have this much spare capacity left in my system. That's my headroom. I'm just defining some terms now. I know then that if I track the headroom, the amount of spare capacity that I've got, and I've defined my capacity based on some set target KPI, or in Max's terminology, some business decisions, then I know how much headroom I've got, and if I track it over time, forecasting when that headroom is going to run out gives me a capability to do just-in-time capacity expansion. So, what do I mean by user experience-based KPIs? Well, there's all sorts of different KPIs we can look at. We can talk about coverage, we can talk about resource utilization, service availability, service retention, and different types of throughput. I've indicated on the left-hand side the ones that I think are really user experience KPIs. Users care if they can't get serviced. Users care if their service gets dropped halfway through an instantiation. Users care about the throughput that they personally receive. They care about getting throughput during those moments when they're interacting with the service. They do not care about engineering terms and resource utilization and how much downlink power is being consumed at the node B. They do not care about peak user throughput because users never get to experience it. They care about being able to get that interactive throughput even during the busiest of hours. So really, I can dimension my network to meet any given set of these user experience KPIs. Those are the business decisions that Max was talking about. Having chosen those business decisions, those key target KPIs, then the idea is to then build, using our tool hopefully, a methodology for managing that capacity. Here's another example. I've now got two different types of service. I need to support signaling and I need to support data. If I only considered a signaling load, then there's got to be some maximum engineered capacity there, a yellow star on an axis. Similarly for data load. Therefore, the combination of these two, if I've set my target KPIs, say for service availability and interactive throughput, there's going to be a combination of signaling load and data load that my system can support. Therefore, there's this admission region boundary where if I measure signaling load and I measure data load, I know I've still got spare capacity and I can measure headroom, headroom being the distance to the boundary, the distance to the exterior of that green region is my headroom, my spare capacity. The problem is I don't know really what the shape and size of this admission region boundary is. It could be very heavily convex or it could be very heavily concave. And getting the shape and size of this wrong has a very large impact on the way you manage capacity. Soft capacity that Max was just talking about is where even if you are monitoring these emission regions and predicting how they go, under different radio conditions, you could have an emission region boundary out here at this blue boundary, or it could contract further. Soft capacity is the breathing of the size of these emission region boundaries. So under different radio conditions, we've got more or less capacity. So the exact shape and size of this emission region are unique to each cell, unique to the way you've set your business decisions, unique to the way you set your target KPIs. And they can really only be determined by modeling. Here's a real-world example. This is for a customer that we installed our service Thames Capacity Manager on in 2014. They had nearly 15,000 cells. I have normalized the axes intercepts on these emission regions to the 1.0 on each axis, but you can see that the shape and size of the emission region boundaries varies significantly. We've got quite a few that are very heavily convex, which is great. That means that the schedulers in this particular UMTS network are working efficiently. We've got several, though, that are very heavily concave. And it's these ones that we have to be very careful of, that we're monitoring soft capacity appropriately. We're tracking headroom so that we can work out a time to do just-in-time capacity expansion. Because if we're not modeling soft capacity, then we're really kind of dimensioning just to this straight line diagram. And if you think about that, we're probably making a capacity expansion decision incorrectly for every single one of those cells in the network, because not a single one of them has a straight line. The various factors that affect capacity, obviously spectrum availability, how much spectrum do I have to utilize, the utilization of UMTS codes and physical resource blocks and LTE, downlink power, what type of scheduler algorithm I've got implemented, the various QoS settings and call admission controls that are implemented in my network, how am I setting the ARP scheme, allocation, retention, prioritization, what level of resource reservation do I have set to allow for handovers and for signaling traffic. And obviously the radio environment, the soft capacity situations, weather, user location, user demand and interference. There could be hard limits on the number of LTE users. There could be hard limits on the number of HSPA and EUL users. Obviously there are licensing issues with your vendor. There's limitations at the computational processing power in your baseband. And obviously all of this traffic needs to be backhauled towards the core of the network, so backhaul bandwidth also becomes a factor. The bottom line is this modeling of soft capacity, the modeling of capacity in your UMTS and LTE network is a really, really complicated beast, and all of these factors need to be taken into account. I got a question just talking about my previous slide on HSPA Erlangs. HSPA Erlangs I was referring to were simultaneous HSPA users in the scheduler and just normalized to the value of 1. So the bottom line in all of this, and this is the last slide before we get to Q&A, we claim that Thames Capacity Manager is a tool that does all this stuff. It delivers optimized capacity management. It understands how your network is currently loaded. It has models of soft capacity that is being tailored to every single network element in your network. It understands resource allocation. It understands how the different vendors do radio resource management. It understands how they provide service to the end user. Having all this, being able to predict emission regions, shapes and sizes, being able to track headroom values allows for just-in-time capacity expansions. It identifies the capacity constraining resources, so you can start planning capacity expansions based on the output of Thames Capacity Manager. But it also enables very detailed scenario analysis, because we have customized models for every network element. Then we can apply those. We can apply changes to those models, so we can do what-if scenarios. What would happen if the level of HSPA traffic doubled next year? We can run those models because we've got the customized model. We can run that scenario to test things. All of this enables really intelligent business decisions, just-in-time capital planning, prioritization of where to spend your money under different metrics. But it really comes down to consistent and systemized planning across your entire business. So at that point, I think we'll stop and we'll open up for questions.
Thank you, Bruce. I fact, you already started answering this question, which is great, and we're getting a lot of them. So thanks for the audience for participating actively. Just a reminder, because I get this question frequently, the slide deck and the webinar recording will be available within the next 24 hours. I'd like to invite Caroline back to act as a moderator on the questions. Thank you.
Great, thanks, Adeline. Yeah, we're getting a lot of questions here. Sadly, we won't have time for all of them, but I'm going to try and consolidate a few similar ones so that we cover some ground, and hopefully some of the more specific questions we may be able to address offline after the event. I'm going to start with a fairly general one that I think both the panelists can probably comment on. And by the way, thanks for two really interesting presentations. In general, we hear that network hardware is getting progressively cheaper, and we're even moving towards very new architectures like Cloud RAN. So in those situations, will it be so important to prioritize capacity in this way, or in a way are we now at the peak of what operators need to do and the task is going to get easier? What's your comments on that? Perhaps Max, I can ask you first.
Absolutely. Thank you for the question. It's a really, really good question. I think that it would be wildly optimistic to assume that things are ever going to get easier for us. With cheaper hardware, that is countered by the dramatic increase in the amount of traffic that we're offering, that's being offered to networks, and in the number of network elements. As we move to 5G with the Internet of Things, we're going to have many, many, many more devices. I mean, previously, 10 years ago, you were lucky if a person had one mobile device on them. Today, people might have a phone and a tablet. In a year's time, they might have a phone, tablet, and a smartwatch, and the number of devices that people are carrying on them is also going to increase. So the fact that we've got more and cheaper network hardware doesn't mean that we don't still need to understand exactly where and when we need to provide additional capacity. I think that it'll change the way that we need to model things, but I think the fundamental idea that we need to identify locations where stuff is performing badly and target the money that we spend there is going to remain the same. Just the actual scale of the problem that we're dealing with is going to become much greater, larger, and harder to manage without having appropriate tools that can automate some of this task for you.
Great, thank you. And Bruce, any thoughts on that one?
Yeah, my only extra comment to add to that is one of the major costs is also the spectrum that the operators are purchasing. And if we're not making very intelligent decisions about what regions we need to purchase spectrum in the various auctions from our regulators, then we're doing ourselves a disservice. So you really need to have a very good understanding of your capacity situations tailored to the individual cells in the various regions before you can aggregate that information up to the region level to start bidding into spectrum auctions.
Yes, it's very true, and sort of perhaps related to that, there's several questions regarding the changing nature of the access network, not just in terms of the types of base stations, but also operators looking at two things, having to plan for Wi-Fi, so offload and Wi-Fi calling and so on, and also having to take into account quite a large number of legacy spectrum bands which may be refarmed for LTE. So I'm wondering if you have comments on what challenges that raises for dimensioning, so including Wi-Fi in the mix and including refarming the legacy bands. Perhaps we'll start with you, Bruce, on that one.
Yeah, so refarming, once again, your models if your models already have a customized view of capacity cell, then you can also use those models to estimate what would happen if you refarmed spectrum to make it available, say, from the 2G band, you release some GSM spectrum into the LTE band, then you can see what would happen if you'd added that spectrum. That also provides greater insight to your higher level managers when they're bidding in spectrum auctions. all of this stuff can be made available. It is not possible to do that very effectively unless you understand the soft capacity situation. I think I'll let Matt add to that if he wants.
I was just going to say Wi-Fi is a perfectly Wi-Fi offload, a perfectly legitimate way to manage capacity, and it is also something that needs to be considered by your dimensioning processes. You don't want to be offloading people onto Wi-Fi and giving them a really crummy experience. You need to also have models in place, and these models will do the same sorts of things, but the technical details will be very, very different to those models that dimension licensed spectrum. Similarly, with up-and-coming technologies like LTE-U, where we're able to utilize unlicensed spectrum for LTE transmissions. At the end of the day, the focus really is on the customer. We need, regardless of which access technology we're sending the customer to, we need to be ensuring that they get a consistent user experience and the best user experience that we're able to provide them.
Excellent. Quite a few questions relating to how you actually define user experience. All the speakers have talked somewhat about that, but one that struck me as interesting is speed the actual one of the really defining characteristics for user experience, or is it more important to have consistency? So if a user gets a very high speed in a non-busy time and then doesn't get it in a busy hour, is that worse than giving them a slightly lower speed that's consistent? And can the tool be easily adapted to change that priority if the operator decides to?
It's a tool question, I better answer it. The user experience targets that you can set, obviously on service availability and maintainability. Also, one that we recommend to our clients is that they set a target for interactive user throughput. That would be the throughput that the user is expected to receive when they're interacting with their services. That means when they've got packets in the network element ready to transmit or receive. It's network monitoring tools. They can report on performance counter information that are long-term averages over 15 minutes or higher. They're not reporting the individual user experience interactive throughput. The tool can get an entire histogram of expected user experience based on interactive throughput. So we can set targets for the 90th percentile user. We can set targets for the 10th percentile user. So perhaps if we want to get that 90% of the population is going to get at least 200 kilobits per second on HSPA, but in those really good times, if you're a top 10 percentile user, we want to hit something like 3 megabits per second. So we can have these sets of target KPIs that then all join together to form the target KPI set against which we derive admission region boundaries and calculate headroom. Then we can start tracking that headroom, and it's inherently taking into account all of those things. So different speeds can be set, different speed targets, and it all comes down to setting a consistent set of targets so that your entire dimensioning process is defined by those, and then you keep tracking it for just-in-time expansion.
Great, thanks for that, Bruce. And unfortunately, we've gone past the top of the hour. I think we've had loads of questions, and I know we could carry on discussing these issues for another hour, but everyone has busy lives, so unfortunately I'm going to have to wrap up. Would like to say that Ascom Network Testing and the rest of us will try and answer some of the questions that we haven't got to today by email, so we will try our best to address the questions because we appreciate all the interest that's being shown by the audience today. But I would just like to say thank you very much for attending and hand back to Adeline to wrap up.
Well, thank you, Caroline, and thank you, Bruce and Max. You guys did an amazing job presenting today. It is a fascinating subject, and that's proven by the number of questions coming in. And so I want to thank the audience for participating, and we will try to follow up on those questions directly from the Ascom team. And I want to thank Ascom for sponsoring this webinar today. And again, all the material will be available in the next 24 hours. I promise that. And so thanks, everybody. Have a good day or a good night, or depending on when you are. Thank you all.